But let me introduce you to Martin R. Schiller. He's not a physician. He's listed as an MD, but he's not. He's PhD. Come on up. He's the executive director of the Nevada Institute of Personalized Medicine. His talk is on personalized medicine. He's got a BS from Hofstra University and a PhD in biochemistry from Utah State University. He served as faculty at Johns Hopkins, University of Connecticut Healthcare Center, and he's a professor at the University of Nevada in Las Vegas. His research focuses on building scientifically tested sequence and structure-based bioinformatic tools and their application to various diseases, functional genomics and human genetics. And he's published 64 papers, and he's a fascinating scientist. I'm sure you're going to enjoy Martin's talk. Thanks, John.
Thank you. We'll start it off the talk with a question. How many of you or your patients would pay an extra $100 for 15 years of life expectancy? It's a good layup for me, right? How many of you think you've already done that? You have. So if I put this plot together about 10 years ago, and I find myself using it quite often. What's shown is the life expectancy of a human over the past 4 millennia. And if you fit the last 50 years of this curve, which is in blue, for every year you live, you gain about 2.2 months of life expectancy. If you calculate how much money we've invested into research in the biomedical realm over the past 100 years, it's a little more than $1 trillion. Using those numbers, you basically have paid about $100 for 15 years of life expectancy. It's not very well known, but it's pretty surprising. So when I looked at this curve and I'm thinking about where we are today and the trouble we're having with our healthcare system, and I look at this plot, it's really working pretty good at a global level. We've got a fantastic trajectory. But where are we going? And that's kind of why we're involved in research. And in order to know where we're going, it's helpful to look at the past. If we're looking 1,000 years ago, the life expectancy was 30 years old. So we've come a really long way, but we are driving this curve currently, and what sorts of things are likely to drive it. And as you're all here, I think concierge medicine is what's going to start changing things. But I also believe a lot of recent work in what people are calling personalized precision or individualized medicine will be playing a role as well. And I'm here today, I think, because one of the possible platforms to launch this, which it really hasn't launched in a big way yet, could be concierge medicine. Okay, so let's just do a little bit of human genetics to get everybody on the same page so we can understand what is personalized medicine. So we each have 23 chromosomes, and if you look at any one of these chromosomes and expand out a small region, it is just a sequence of base pairs, GATC, which is shown here. And if we sum up all of this, humans have 2 copies of 3.1 billion base pairs. Okay. Now, as we've begun to sequence people now, what we get are variations. So this would be a variation that's different between person 2 and person 1. And there are lots of variations. We've already seen from sequencing over 1 million people now, there's about a little over 100 million variants. 4 million of them are very common in the human population, and the others are quite rare. So if we just make a rough plot of human history here, with this would be genetic Adam and Eve, that's about 6,000 generations ago. And as you go down, if we accumulate a variant at some time in history, all of the progeny, or not all of them, but a lot of them are going to end up with the variant. And so we end up with, if we had a variant born back here, right, we're going to end up with that variant being prevalent in a whole race, okay? If we have a variant born very recently, it's going to be in a clan. I notice on the agenda there's another Schiller speaking. It turns out for people with fairly uncommon names, 30 to 50% of them tend to be related in history and don't know it. I'm probably related to this Mark Schiller who will speak tomorrow. The other thing is for you, every person born gets 50 new variants that you get to own. They're unique to you. And they've probably only ever been seen a few times in all of human history. Okay, the other source of variation comes from us interbreeding with other hominids in recent history. So basically we've bred with two types of hominids. Almost everyone in this room, well, no one in this room for what I see is all human, even though you think you are. You all have a couple of percent of, or close to that, of Neanderthal variants in you. And then there's another species called denosovans, and people have as high as 4% denosovan in them, and that's more concentrated in people from Southeast Asia and the South Pacific. So everyone is a hybrid of Neanderthal except for a few small tribes in Africa, and then we have all of these people living in Southeast Asia, the South Pacific, American Indians that have high concentrations of denosovan alleles, so they're tribrids of these hominids. So there are alleles that come that are very positive and affect good outcomes in humans from the hominids. Even if you go to a third cousin, a distant cousin, they have a lot of variants in common with you. Okay, so here's the protein change, and so now if we look at all 23,000 genes, they combine in each cell into this network of proteins that control the chemistry of the cell and everything else. And it's when this network breaks down that we get disease, when there's a mistake. Okay, so now moving off genetics and into personalized medicine. So the average person sees a doctor 4 times a year. The effectiveness, dependent upon specialty, ranges in general from 30 to 50%. And if we look at the expansion of healthcare from the video from 1,000 years ago, where we have very primitive treatments, bury them in the marsh and treat them with this poultice, and kind of diagnoses and prognoses that seem stupid today. We've now progressed to this being almost out of control to manage for a primary care physician. We have 18,000 diagnostic tests. We have 12,000 named diseases. We have 1,000 drugs approved by the FDA. And so it's become a lot more difficult to manage. Thank God we're in the information revolution where we have a better means of managing this. And so I think that the goal of a lot of improving healthcare is to go from kind of a trial and error sort of medicine where we treat people in the primary care, and then if it doesn't work, we try an alternative and continue in that way. Then you get referred to a specialist, you get more tests, and you go down this path. And some people end up searching the healthcare system for their whole life, because if they have a difficult, undiagnosable disease, they have a chronic condition that they're going to be, probing the network for quite some time. So we've seen some data-driven medicine already this morning, but the idea is if we can do it for shopping, right, where we're using all kinds of data to make you buy more stuff, why can't we get this working much better for medicine? And we think that genetics needs to be part of that. Okay, so what's the impact so far? There are about 8,000 germline Mendelian disorders that are known, and about 4,000 of them we know the variants that can be causative of those diseases. While any one is very rare in the population, collectively they account for 10% of people. So using the genetics to take this very rare disease and help with clinical decision making is very relevant to be used and could be used in practice much more broadly today. Prenatal testing, this is basically replacing amniocentesis. If you sequence mom's blood, you can see the genome of the unborn fetus, okay? And this is slowly replacing amniocentesis. Well, not slowly, more than half of amniocentesis has gone down more than 50% in the past few years. So it's replacing that. It's used for diagnosing dysmorphologies. It's the standard of care in cancer therapy. You really, to know what drug to give, you have to understand what genetic pathway is perturbed in the cancer. And in pharmacogenetics, it's being used for effectiveness, dosage, and adverse reactions. It's also starting to find its way into using lots of variants to calculate risks for common disease. And this will be growing a lot over the next few years. It's minorly used for surgical outcomes and in preventions. Okay. So there is a registry of all these tests, and there's a summary here. I just put it up. There's an example on the right where you would run this panel of all these genes in colon cancer to identify risk for colon cancer. So that's like an example genetic test. But obviously there's a ton of these that are available, and there's 477 labs in the country conducting these tests. The way it works is you could take a sample such as spit or blood or a biopsy. You prepare a library, which is, I won't go into. Then on the instrument, it reads the sequence, and then you basically do analysis. And then you can do secondary types of analysis by using databases of known variants that are connected with disease. Okay. Now, the FDA kind of doesn't like this being used in a clinical setting so far because of the fact that it's tough to interpret. People could make decisions on their own if it was a direct-to-consumer test without any input from a physician or a genetic counselor. And there's a huge danger in that. And so at the moment, the brakes are on, but it can be done in a research setting. That said, it's going on at most major medical centers in the country. Some degree of personalized medicine research or an institute similar to the one we have here in Nevada. Another way it's being used are in what's called genetic odysseys. And if you sequence a trio, which would be the affected, their mother and father, you can, if you have an undiagnosed disease, you can, in half the cases at some clinics now, narrow it down and get a diagnosis, and then in some cases progress on to treatment. So it's providing a venue to assess this smaller portion of patients that don't kind of fit into what we already know clinically. There's a list published by the American College of Medical Genetics called the ACMG 55 list, and these are 55 disorders where if you're doing something else in your clinic and you have an incidental finding where you identify this, you would be obligated to report that to the patient because it's a dangerous mutation that's likely to cause disease. The other thing that's expanding, where this data is just going to exponentially grow, are genome-wide association studies. And what these are, I'll go over in a second, but just to give you a little bit of background, if we look up, I twisted the slide. There's been about 2,000 studies as of 2014, and it's growing quite quickly, but on the chromosomes, you could see all the loci where something's been linked to one of those types of diseases. So the amount of information we're gathering where we can link a variant in a person back to something that's clinically relevant is growing very quickly. Okay, so what are the limitations and why is this not more broadly used at this point? One of the major challenges are called VUSs, or variants of unknown significance. So this is one of the most popular genes that's sequenced. It's BRCA1, and Myriad's a company that has a clinical test, and it's related to breast and ovarian cancers. And if you look over at the pie graph on the right here, what you could see is that, there's 2,200 variants in these two genes, and the genes have about 12,000 possible variants. So about 1/6 of them are known to be pathogenic, and they affect the function of the gene. But most of them, we don't know. And so like if you have a rare variant that comes up in BRCA1, even if you have a family history of breast cancer, there's no help that would be gained from this test. So that's one of the limitations. A lot of mutations and a lot of genes fall into this category. But my lab's actually working on a new method to assess VUSs, just to let you know. So there is research going on in the area. The other problem is there's no model for the payers yet. It's really, without that, it sits in a research setting or it gets funded by the state or whatever. And so no one's really come in and demonstrated ROI, right, where you can get a good ROI from doing this, except maybe in an isolated study. But with the amount of variance and what's going on that I've shown you, it's kind of surprising. We seem to be right on the verge of this right now. And my question for you is concierge medicine the way that this may become implemented? You are providing a higher quality of service, and this is slowly becoming perhaps part of that higher quality. Okay. So I'm just going to delve a little bit deeper into pharmacology. So 10% of the 1,000 FDA-approved drugs have warnings on their label that you should be doing genotyping before you use the medicine. Most of them are not used in practice. There's obviously another barrier there in having this make its way into the clinic. It's used in 10% of hospitals, actually, to determine drug dosing. Your liver enzymes, your P450s, really determine how well you metabolize drugs that you're given and really affect the dose that's sitting in your blood. And so it's becoming increasingly important to do this. When we talk about adverse events with opioids and other things, a lot of them are caused by getting too much of the drug, perhaps because you're a slow metabolizer and you're getting a much higher dose of drug than someone who's a really fast metabolizer and clears it from their blood quickly. I spoke about the diagnostic odysseys. That's also relevant to pharmacology. I'll give an example about opioids later. You get drug-induced diseases like liver toxicity where it's relevant, and then, but it's still not being used more broadly. And my bet is that not many of you are using pharmacogenetics for prescriptions as well. But are you? Okay, starting to. Yeah, okay. Okay, so this is what's known. You can go to this database and pull up all the information I'm going to show you in the next couple of slides. But genetics plays a role in dosing of 68 drugs right now. And it's overseen by these entities. And these are the genes that are in your liver that basically oxidize and help you eliminate drugs in your urine. Okay. I'm going to give one example because this is something that should probably be used in all clinics today. But again, it faces the same thing. It's on the label and it's not being used. So CP219, clopidogrel is used, or Plavix is used in many surgeries. And all of us are going to have some surgery at some point. And it turns out that when Plavix gets processed, there's an enzyme, the CYP2C19, processes clopidogrel in a prodrug form into the active drug. So if this enzyme doesn't work, you never get active drug in the blood. Okay, so you're not getting protection against embolism and stroke, which is what the drug's for. So if you look at the variants, which are given these star names, if you have these combinations of variants, you would be an intermediate metabolizer, okay, which means that you're not going to produce a lot of drug, but you're going to produce an intermediate amount. 18 to 45% of all patients fall into this category. If you have these alleles, you're a poor metabolizer and you get almost no drug. You shouldn't be using this. You should be using warfarin instead. This is 2 to 15% of people in the population. But if you're Chinese, it's 14% of Chinese, okay? And then so it's not just for this drug. This gene actually affects 5% of all drugs in use, okay? So this is just one snippet of those 68 places where genetics should be playing a larger role in pharmacology. Okay, so a quick example of a diagnostic odyssey and how you may take advantage of it. The NIH has formed, I think there are 6 centers in it now, an undiagnosed disease network. So if you have a patient that can't be diagnosed, they can apply to this network and get treated there. And so in this network, up to 50% of patients that are accepted, it's really 30 to 50%, can get a diagnosis by genome sequencing of the trio. It ranges from 24 to 50% depending upon the center. And like another example here is that was found in one of these diagnostic odysseys is that some people have mutations in receptors and may be completely refractory to opioid drugs. And there was a recent publication where, I forget what this person had a severe pain and it couldn't be alleviated at all by opioids, so they were just popping ibuprofens, and that was somewhat effective. And when they sequenced them, they found a mutation in the opioid receptor gene. This would be one of those 50 unique ones you get yourself. And in a lot of the undiagnosed diseases, or at least half of them, they're popping up as being these super rare variants that are unique just to that person. Okay. And so like there are other P450s that, basically are involved in morphine metabolism. So, all right. So I want to wrap this up by just, making a pitch for the future of this. So 1 in 10 people are going to have one of these genetics playing a role in their disorder. If you map the number of states that have very few clinical geneticists with the ones that don't receive NIH funding, those are shown by the hatches and the green symbols. And what you're left with in gray are the major medical health center states. So the genetics is starting to find its way into the clinic, but only in those states. And there's a concern, I'm here in Nevada, I think, we're really getting left behind. Nevada had 2 clinical geneticists for a population of 3 million people when we started our institute. And that's our goal, is to be impacting this, especially when you consider how many people need the care. And our clinic has been doing pretty well, even though it's only been up for a couple of months right now. So what do those states do is they tend to just export the healthcare services to the neighboring states, or people don't get the services. Okay, so I just wanted to make a pitch for our institute. We started just 18 months ago. Here's our mission statement. We have people doing GWAS on schizophrenia and smoking addiction. This group just published a paper where they have a variant that highly partitions into smokers, but you don't find it in the general population. So it can be predictive of someone who's going to become a lifetime user of cigarettes. This MIRA works on transposons and also on using genetics to look at, to diagnose cancers with unknown primary origins. Michael is our clinical geneticist, and he's starting up Ehlers-Danlos syndrome clinic and research. I work in functional genomics, personalized diets, and variants of unknown significance. Ching Wu is doing personalized reference ranges using bone mineral density as a model. So there are people that have high cholesterol that are just fine, and there are people that have low cholesterol that get huge plaque buildup. And he's building algorithms that use the genetics to adjust the reference ranges. So on the clinical report, instead of getting a global range, you would get your personalized range that you're trying to be within. And then we need to do a lot of genomics, so we have a big data scientist who's an expert in algorithms as well, Justin. We are really interested in personalized medicine and concierge medicine. We've been talking with Rob Rowley, and we're interested in maybe looking into a research study to more broadly implement this, where our institute would work with several of the doctors. If you're at all interested in that, or just want to learn more or talk about it, you could leave your card today with either Rob, I'm going to take off, I'm late for an appointment already, or Jim Timmons is in our institute, he's in the back of the room as well. And I thank you for your attention, and I'm happy to answer questions.
Yeah, the mic's over there for questions. If anybody has questions, it's a great talk. Thank you.
Hi there. I'm Andy from the Genomic Alliance, for those of you who don't know me. So the Genomic Alliance is a network of hundreds of doctors all across the country using genomics actually every day in their clinics. So this is actually happening in real life. It's a great talk. Thank you. Okay. So a surprising number of people who do full-scale, full genome testing actually have a life-changing result. And I just hope everybody appreciates that. About 45% of people who do whole genome are starting to get a life-changing result. I had a life-changing result when I did my own DNA test. But anyway, so I encourage everyone to join us. Thank you.
Yes.
Yeah, thank you for the talk. It was excellent.
Oh, thank you.
I was approached by a genomics company who told me that they have reimbursement for something PGX testing, the drug-drug interaction platform. They called it PGX, I'm not sure. But they said Medicare did pay for this, and they had a very wild idea how they can interact with concierge doctors, and it really didn't pass regulatory muster. But I was told that this was covered. So you're saying that there's no coverage for the drug-drug interaction genetic platform?
Yeah. That's what they're saying. I don't really know, but I think in general there's a lot of difficulty with coverage, except in cases where, you know, you're using a $100,000 cancer therapy and, you know, you have to genotype before you decide to give that therapy.
Mike, if you're going to ask a question, please do it on the mic. Yeah, they did pay for it, Rob, but they don't anymore. Was doing it in my office, and so was Cindy. Marcy?
But back to that point, I've heard, and Jim may know the company, there was a company that was saying that they would do the testing, but if Medicare wouldn't pay, they would pay. Okay, so I wish I could, I saw that in the last 6 months. I forget, do you know who it is? It could be Geisinger.
As concierge physicians, I'm going to be very controversial. Who gives a damn if they pay for it? Paying for it is an insurable thing. Insurance is not to be paid for in preventive care. Preventive care is not an insurable event. It is not. Insurance is an actuarial bet. You get insured against, God forbid, cancer. This is not an insurable event. So we need to post the prices. Competition will bring them down. We need to tell our patients why they need it. That's our business, to sell the value of the product we're selling, period, the end.
If they're coming to you and paying more for concierge medicine, this is the group of people that's likely to pay more to sequence your exome. In the research setting, this is going to be like, you know, $400. The clinical test will obviously be more expensive, but if we conduct collectively a research study on the impact of exomes and providing a lot of this information, we're assuming for that cost that a patient that's willing to pay extra for medicine and is likely to have this impact their care would probably be willing to pay the extra cost.
So we have Eden here from Invite, who's, I'm sorry? Invite, I'm sorry, Invite, who's given us a grant and is in the hall down here, the other hall. Please, she's got a product for $400 and some that covers just about everything. It's a pretty amazing product. I talked to her this morning. Be sure you talk to her. It's something you could use in your practices.
Yeah, hi, I'm John Kim from Durham, North Carolina, and I practice internal medicine. So, you know, my life is in the trenches, practical. So can we just order gene testing through like LabCorp or Quest, or do we have to figure out which of the 400?
Yeah, well, you can order, so Quest has a wide array of genetic tests, and then there's GeneDx and other companies. If you're comfortable interpreting the test, then yes, you can just order it and go ahead. But you might need the assistance of, you know, a clinical geneticist or a genetic
all those
chemist.
labs have pathologists and experts, you know, available for consultation. Okay, that's good to know. Next question. I do a decent job in neurology, and a problem that I have in my area, although there are thousands of physicians in Durham, Duke, you know, and Raleigh, UNC, the area, and all of us, I'm sure, have no specialties that are weak. In my area, it's neurology. And so what I find, I do a decent job at neurology, so if I can't diagnose a neurologic problem, at least 8 times out of 10, none of the neurologists I refer my patients to can make a diagnosis either. And so I'm wondering if, is there a role for this testing in my situation? How good is gene testing for, say, neurologic conditions, and et cetera? Because it's, you know, it's abysmal, the, you know, the help that I can get from the consultants that I use.
Yeah, so I think this is one of the areas in the undiagnosed disease network that they look at. So I think there is a value there. And, you know, the network started at NIH a few years ago, but it's expanded now, and I suspect it will continue to grow. So it's probably something you could tap for that.
Take the mic. One more question, and then we got to move on.
It's just a comment. you know, the one thing is the state of Nevada actually has a law that you have to do a separate consent for genetic testing, which is so commonly not done. So it's just one of those things that you want to make sure that you get from one of these labs, that you get their consent form, that they understand the risk and benefit of doing genetic testing. And with North Carolina, I would guess they would have it, because Nevada usually trails and things like that. But
Thank you. Thank you, Dr. Schiller. That was a great talk, and I wish you could stay around and answer questions for people privately.